Okay, last time we discussed we actually started the second order differential equation related circuit or the second order circuits. So it's second order circuits. So how do we characterize the second order circuit? So either the response means the current or voltage. We can basically represent this response as a second order differential equation. So the ultimate response is something like that: d squared x t over dt squared plus a1 dxt over dt plus a naught xt equals ft. So here this xt may be the current or voltage response, and ft is the force term. So this is basically a second order differential equation, and like in the previous cases, if ft is 0, so we can simply claim that this particular circuit do not have any external sources. So ft is actually kind of a constant. So we can claim that this circuit has DC sources, has external DC sources. So if this ft is a kind of function of time, so we have kind of AC sources in the circuit. So this is the three scenarios we can discuss by looking at the component ft, or the right hand side of the differential equation. So then we found that in general, so we can get the characteristic equation. So we can get the characteristic equation by replacing this nth order derivatives with x to the power n. So we will get the quadratic form for the characteristic equation. So how do you get the characteristic equation? First, let ft to be 0. So then we have a second order differential equation without having this ft in the circuit equation. So we have right hand side, and we have a 0 right hand side. So then this characteristic equation can be easily obtained by this particular substitution. So this is the substitution actually. Nth order derivative can be replaced by s to the power n. So with that, you can simply convert this differential equation to the characteristic form. So then we claim that, so this is a quadratic equation, or the equation with a second order. So in general, we should have two roots. So for this case, so we have two roots, S1 and S2. So then depending on S1 and S2, we can further classify the response. So we can basically split into three groups depending on S1 and S2. So the first category, S1 and S2 are real and distinct. So then we have two real roots, but they are not equal to each other. So the second group, so S1 and S2 are real and equal. So we basically ended up with real roots, but the values of these true roots are basically same. So this third is basically S1 and S2 are not real, they are basically complex and conjugate pair. So depending on the quadratic equation, so we can simply claim that so everything depends on this one. So this is some delta. So depending on this delta, so for this case, so delta is actually greater than 0. For this case, delta equals 0. So this case, delta less than 0. So then this, so the roots actually so these are the two roots, and this is the delta term. So this is the delta term. So based on this delta, we can simply categorize into three. So this is the discussion we had last time. So similarly, so we can introduce two new variables. One is called omega naught. So this is the natural frequency of the circuit. So this is natural frequency. So the other thing is like zeta. So zeta is the damping ratio. So we can bring two new variables into this discussion. One is this natural frequency. The other one is zeta, the damping ratio. So we'll see what's the relation of this damping ratio and natural frequency for this particular circuit later on. But so if, and from with these two parameters, we can simply get the characteristic equation. So if you have these two parameters in your system, so this is the characteristic equation. S squared plus 2 zeta omega naught S plus omega naught squared equals 0. So this is the characteristic equation as a function of omega naught and zeta. So this is the characteristic equation as a function of coefficients of derivatives. So we can have two set of characteristic equation. One is actually coming from the coefficients of the differential equation A1 and naught. So this A1 and A naught are basically depend on the circuit component. So if you remember the previous example, so these A1 and A naught and even Ft, so they are basically functions of R, L, C and the sources we connect to the circuit. So this A1 and A2 itself are functions of the circuit component RLC and whatever the voltage or current sources we connect to the circuit. And again, we can build the same characteristic equation as a form of omega naught and zeta. So the natural frequency and the damping ratio. So then these two characteristic equation represent the same system. So then we can easily equate these coefficients and get some relationship in between this omega naught and zeta and A1 and A naught. So by looking at these coefficients, we can simply uh, get two equations. One is like we can easily get the natural frequency by taking the square root of this zeroth order derivative term. Like this. So omega naught squared should be equals to A naught. So then from this, we can easily get the natural frequency of the circuit by taking the square root of A naught. So similarly, we can take the zeta. So from here, we know that 2 times zeta omega naught equals A1. So A naught, omega naught is square root A naught. So from this, we can basically get the value for zeta. So it's equals to A1 divided by 2 root omega A naught. So then with these two relationships, so you can easily find the natural frequency and the damping ratio for a given circuit as a function of circuit components R, L, C and the values of sources. So then if we find the delta for this particular formula, so this is actually so 4 zeta squared omega naught squared minus 4 omega naught squared. So from this we can take this 4 times omega naught squared zeta squared bar. So this is the delta in the form of omega naught and zeta. So then in addition to this delta, which basically calculated from A1 and A2, so we can split into these groups based on the value of zeta. So for example, so the first case delta greater than 0 means, so if we want to classify these three scenarios using zeta, so this basically refers zeta greater than 1 scenario. So this refers to zeta equals 1 scenario. So this is zeta less than 1 scenario. Okay. So then if this damping ratio is greater than 1, so if this damping ratio is greater than 1, we can simply say that, so it basically has two real distinct roots. If zeta or the damping ratio is equals to 1, so this is like you ended up with a kind of a real equal roots. Less than 1, so you have complex and conjugate roots. So then depending on the zeta value, we can define or classify these three scenarios like that. If zeta is greater than 1, so we can simply say that this is a kind of overdamping system. system. So we'll see what's the difference between this overdamping and other scenarios. So overdamping system. So if this theta equals 1, so the damping ratio is equals to 1. So this become a critically damping scenario in system. So the third is actually under damping system. Then depending on the theta, you can basically classify this second order circuits into three classes. One is this over damping, then this critical damping, under damping. So we can easily get this three systems classified based on the theta or the damping ratio of the circuit. We can evaluate the damping ratio once we get the differential equation. Just map this coefficients of this first order and zeroth order derivatives as this one. So then we can easily get the natural frequency and the damping ratio. So if you know the damping ratios, you can basically get the values of theta, and based on the theta you can decide the nature of the differential equation of the roots. So if this theta is greater than 1, we can basically say that this is a kind of a system where you have this over damping scenario. So theta is 1, so it becomes a critical damping scenario. Less than 1, it becomes a under damping scenario. So then depending on this damping, so you will ended up with three type of responses. So you'll ended up with three types of responses. So we basically discussed one last time. So we know that depending on the classification, so S1 and S2 may be in general a kind of a complex number. So the S is actually sigma plus K omega. So it's in general a kind of a complex number because two scenarios are simply discuss about real roots, and the third scenario is discussing the complex root. So if you basically define this S as a complex number, so we can treat these three scenarios simply. So then if this omega equals 0, so then S become a real value. So if omega is there, so if omega is not equals to 0, S become a complex value. So this is very simple. So in general, we can redefine S as a complex number. So then we know that for this differential equation, so the second order differential equation, so we have, so this is your differential equation. So then if we want to evaluate the natural response, so we let ft to be 0. So then our modified differential equation would be in the form of this. Equals 0. So your right hand side should be 0 because we need to simply neglect the impact of these external forces. So once you remove the impact of external forces, you can simply think of how we can get the natural response, which is basically the impact of the initial conditions of the circuit. So this is the modified differential equation targeting to get the natural response. So this is, so we want to get the natural response. So let this ft or the force time to be 0, to be 0. So then we can get the modified differential equation having this 0 from its right hand side. So then we can easily get the characteristic equation. So this is the characteristic equation. So this is the characteristic equation. Yes. Now, so we know that. So for the first order differential equation, we basically ended up with this kind of response. So this exponent term we basically obtain by solving the characteristic equation. So this exponent of the solution, so x and t, natural response, can be represented as a kind of an exponential function k e to the power st. So s, which is the exponent of this solution, can be obtained by solving the characteristic equation, or else we can simply say that s represent the roots of the characteristic equation. If you found the roots of the characteristic equation, so you can simply plug it to here and get the response. So if it is a first order circuit, first order, so your characteristic equation would be this kind of. So then the root of this s is minus a naught. So then you just plug it to here and you can claim that the natural response is in the form of k e to the power minus a naught t. Then you can find the k value by substituting initial conditions to be accepted. Similarly, for this differential equation, we found that, so the general solution, so the general solution would be a kind of this k1 e to the power s1t plus k2 e to the power s2t. So this S1 and S2, so S1 and S2 are the roots of the characteristic equation. So if you get the characteristic equation and solve it and you can get the roots, you can just plug it to the exponent. So then you can get the response. So then the response would be, for this case, your response would be k1 e to the power s1t plus k2 e to the power s2t. So this is the response. So similarly, you can find k1 and k2 by substituting initial conditions. But keep in mind, so you have two unknown coefficients, you need two equations. So two equations means you need two initial conditions. So otherwise you cannot find K1 and K2 both. So or else like you can have a kind of a single initial condition, but using the initial condition, So there may be a possibility to find another kind of initial condition of the circuit. So ideally, you should have two initial conditions. So these two initial conditions may be given in the question, or else you can find the other initial condition by using the given initial condition. So if you go through these examples given in this slide set, so you can see like how we can manipulate these initial conditions to get this K1 and K2. Okay, now for the first case, it's very simple. So we have two real and distinct roots. So you have S1 and S2 separately. So those are real. So we can easily get the response for this first scenario where theta is greater than 1 for the overdamping scenario. So the overdamping scenario, so we can get the natural response like this. K1 e to the power S1 t plus K2 e to the power S2 t. So this is the response for this first case. So if you plot these two, so it may be either like this or it may be like this. So this case, so this sigma or the real, these S1 and S2 are real. So then this would be like K1 e to the power sigma 1t plus K2 e to the power sigma 2t. So this sigma is greater than 0. So this case sigma is less than 0. So if you have this negative exponent, so then you will ended up with kind of a decaying type of functions. So it converts to 0. So if you have positive values for this exponent, so it's a kind of a exponentially increasing function. So we claim that, so this type of a nature is not stable, and this would be a kind of a stable system. Yeah, so this is the simple difference between these two systems depending on the roots of the characteristic equation. So if these roots are kind of negative values, you can simply claim that the system is a kind of a stable system because the natural response would be a kind of a decaying function. So with the time it converts to 0, or with the forced response it converts to a certain value. So if you have positive roots, so definitely your natural response is kind of exponentially growing function. So this is not a stable one. So it means like you, depending on the initial conditions, the current or voltage is simply increasing and increasing. So this is not stable. So because we know that initial condition is a kind of a temporary value stored in this inductor or capacitor. With these initial conditions, after a certain time, so we know that if it is a capacitor or inductor, so it simply discharges to the rest of the circuit. So then after a certain time, this initial effect of this initial condition should be simply nil. So then the response would be ideally converging to a 0. If it is diverging, so if it is continuously increasing, so this system is not a kind of a stable system. So depending on the nature of the response, we can simply claim that it's a stable or unstable one. So this is the first scenario where the theta greater than 1. So you can claim that it's a kind of overdamping case. So for the overdamping case, your natural response is a sum of two exponential terms. So the each term you can get the exponent by solving the characteristic equation. So this roots are real and distinct, so one root is appear as an exponent of the one exponential function, the other one is simply plug into the other exponential function. So the response would be k1 e to the power sigma 1t plus k2 e to the power sigma 2t. Sigma 1 and sigma 2 are real and distinct roots of the characteristic equation. So the response is a kind of exponential, showing exponential trend because it's a sum of two exponential functions. So depending on the exponent or the sigma values of this or the roots of the characteristic equation, so you can easily claim that this system is stable or not. So next we'll move to the next category. Okay, so the next scenario, what happens? Okay, so let's take this theta less than 1 case. So this is 100 ampere. So we know that if the system is 100 ampere, so we have complex conjugate pair. So we have complex roots and those are conjugate pairs. So it means like, so your roots S are basically sigma plus or minus j omega. So S1 is like sigma plus j omega and S2 is like sigma minus j omega. So these are the roots of the characteristic equation. So for this particular case, omega is not equals to 0 because these roots are complex. Now we'll plug into the general response and see whether we can do kind of a simplification. So k1 e to the power. So now this sigma plus j omega t plus k2 e to the power sigma minus j omega t. So we just plug these two roots to the response. So then we can do a kind of a simplification because this e to the power sigma is common for these two terms. So we can take this e to the power sigma t out. So then we have k1 e to the power j omega t plus k2 e to the power minus j omega t. Okay, so then by looking at this one, so e to the power sigma t, so this is a kind of a real quantity. So this is real. So this is real exponential function. But what about these two? So this is a kind of a complex function. Why we have this complex exponential? So e to the power j omega t is there. So this is a complex function. So we know that natural response is a kind of a real function. So this is a real function. Xn is a real function. So once you connect a kind of a storage oscilloscope, you can simply see the response. So it's a real one function. It's not a complex one. So you can basically plot it in the real domain along with the t time. So you can just plot the magnitude of the response. So that's why it's we claim that it's a kind of a real function. You can observe it through a kind of a storage oscilloscope. So then what happens? So we have a real quantity simply multiply with the complex function. So then the ultimate response would be complex, but we claim that the response of the system should be real. So then, so we have to define this K1 and K2 to ultimately that entire functions to be real. So we have to define this k1 and k2, these two values, to make this entire block a real number. So the only option to make this entire block to be real, so this k1 and k2, k1 and k2 to be complex and conjugates. So if this k2 is actually k1 conjugate, only we can make it a kind of a real function. So this should be satisfied, otherwise you cannot make a real output, a real natural response from this. So then k2 should be the conjugate of k1. So then we can basically simplify this entire block into a real function. How we can do it? So let's assume now we have k1 e to the power j omega t, and k2 becomes k1 conjugate e to the power t. So by looking at this, you can simply claim that this is actually equals to k1 e to the power j omega t two times real. So this is equals to the 2 times real part of this. So we'll see that. So let's assume we have a complex number in the form of a let's see, a plus jb. So what about z plus z conjugate? So this is equals to a plus jb plus a minus j. So this equals to 2a. So this is a complex number. So this is a complex number, z, and this is its conjugate. So this is its conjugate. Okay. So k1 e to the power j omega t is a complex number. So if you take the conjugate, so this becomes k1 conjugate e to the power minus j omega t. So if you take this 2 and sum it up, so you will basically ended up with 2 times the, this is the real component of z. So 2a means a is actually the real component of z. So 2 times real component of z. So if you take this complex number and sum the complex number and its conjugate, so you will ended up with the 2 times the real part of this complex number. So then this become a real quantity. Now this become a real. Okay, so then the solution actually boils down to this. 2 times the real part of k1 e to the power j omega t into e to the power sigma t. So if you further simplify this block, so let's assume that k1 is a complex number in the form of like a1 plus a2j. And this is again, we can simplify that e to the power j omega t by Euler transform. So this becomes cos omega t plus j sine omega t. If you cross multiply these terms and take the real component out, So this becomes a kind of a, so the real component would be, so if you just multiply these two, you can get a real component A1 cos omega t. And if you multiply these two terms together, so you can again get a real function. So other two terms basically represent the imaginary part of this product. So we need this real component. So this is the real component of this. So then basically, so this becomes, so if you absorb this 2 also into this A1 and A2, so then we can simply claim that the response, natural response, would be in the form of e to the power sigma t a cos omega t plus b sine omega t. So if you simply absorb these two also into this A1 and A2, so you can claim that the natural response would be e to the power sigma t into a cos omega t plus b sine omega t. See, what about this? So this is the real part of S. So we found that roots are complex and conjugate. So this sigma represents the real part. See, the sigma represents the real part. So if you get this, like for example, if you ended up with this kind of a root, S equals -1 plus j. So what about the real component? This is -1. This is the real component. This is sigma. So then here it becomes e to the power minus t. So just substitute sigma here. So e to the power minus t. So here, so omega, in this case, omega equals 1. So if you plug it to here, these are the omega. So then this becomes a cos t, because the omega is 1, plus b sin t. And e to the power minus t. So if the roots are like -1 plus j, so this is the solution. So again, you need to find this a and b. So those are unknown constants. So you can substitute initial conditions and get the response. Okay, so this is the natural response for the underdamped case where the theta less than 1 will ended up with this complex conjugate roots. Okay, so this is the second scenario. Okay, done. So the third case, so the third is actually theta equals 1 critical damping case. So here it's kind of a special case. Why it's special? So you have two roots, but they are same. So if you just plug into this general response of this second order differential equation, so where you have two complex functions, two exponentials sum to each other. So if you have a single, I mean two roots, but if they are equals, you have this kind of a function. K1 e to the power sigma t plus K2 e to the power sigma t, because you have two roots, but these are equal. So then you can simplify these two kind of e to the power st with a kind of a new constant. So K1 K2 can be simply summed up. So then you have a kind of a constant times e to the power sigma t. So these two exponents are equal, so you can simply sum it up to each other. So then it becomes a kind of a constant. That constant is sum of k1 and k2 and the exponential term e to the first. So by looking at this one, you can simply claim that this is not a first order circuit, second order circuit, because so this is simplified to a scenario where we have a first order. So the solution is simplifies to k times e to the power sigma t. So this become a first order circuit. So not longer be a kind of a second order circuit. So to make it a second order, so we need to modify our trial solution. So the trial solution would be, for this scenario, trial solution would be a form of this st e to the power st. So instead of constant, so we have a time dependent function. So we have a time dependent function. So then if you refer the slides, you can claim that, so this ht would be a kind of a k1 plus k2t. So this is a kind of a linear function. So previously in the general scenario, this would be a kind of a just a constant. But if you ended up with this real root, but these roots are equal, so this this constant term is simply replaced by a kind of a linear term, k1 plus k2t. So then the ultimate response would be xnt is in the form of k1 e to the power sigma t plus k2t e to the power sigma t. So in addition to this just a constant, we have a t term in the next exponential. So the initial case, you have k1 e to the power sigma t, sigma 1t plus k2 e to the power sigma 2t. So if the sigma 1 and sigma 2 are equal, so this response is simply modified to a scenario where you have k1 e to the power sigma t, and the second exponential is just not a exponential, so it simply multiply with a kind of a linear term t. So then if you take the summary of this stuff, if theta greater than 1, so your xn would be this, e to the power sigma 1t plus k2 e to the power sigma 2t. So for this case, you have two real and distinct root. So the next case actually is theta less than 1. So your response is actually equals to e to the power sigma t a cos omega t plus b sine omega t. So where you have roots are complex and conjugate pairs. So the third scenario, theta equals 1. So then this natural response is in the form of k1 e to the power sigma t plus k2t e to the power sigma t. So we have same root, so the exponent is replaced by the same value. So here real and equal roots. Done. So then, so we can see what would be the responses for these three species. Okay. So the first case, so if you have two exponentials, so two exponentials, so it would be either this form or this form. So this is actually sigma I is greater than 0, sigma is less than 0. So the next one, so if you have this theta less than 1, what happens to the solution? So what would be the solution? So by looking at this, so here you have this a cos omega t plus b sin omega t. So this can be, if you know these values of a and b, so this can be converted into a kind of a sine or cosine function. For example, you can put it like cos omega t plus theta model, or a sine omega t plus theta model, a kind of a cosine or sine function with the phase shift. So this can be like cos A cos B plus sin A sin B model, or else cos A sin B plus sin A cos B model. So then basically we can simplify this term, if you know the values of A and B, to a kind of a sinusoidal excitation, sinusoidal function, cos omega t plus a kind of a phase shift. So this is the real exponential function. So depending on sigma, so this trend is basically changing. So if you draw this one, so this is the envelope. So whatever is cosine and sine. So if we know that if you can simplify to cosine function or sine function, so the amplitude of this cosine and sine simply vary between +1 and -1. But with the product of e to the power sigma t, so with the product of exponential function, so then definitely amplitude may be either increasing or decreasing depending on theta, sigma. So think of this. So this is the so this is the exponential function. So if your sigma is greater than 0, sigma is less than 0. So if sigma is greater than 0 means this exponential function has a kind of a positive exponent. So then the exponential is like increasing. The trend of this exponential is increasing. So then the amplitude of this cosine or sine would be simply increasing. So the function would be something like that. Or else it's, if your sigma is like negative, less than, so this is the response of the scenario. You have a kind of under damping scenario. So this is over damping, so this is under damping, so this is critical damping. So this is the response. If you see sigma or the real part of this root is a positive value, your response is like that. So it's a kind of a sinusoidal trend, but the amplitudes are simply increasing and increasing. If the real component of this roots are basically less than 0, kind of a negative value, so your response is simply converging to 0. So this is the third scenario. Okay, so the third case where your theta is 1, then the critical damping scenario. So you have exponential function and a kind of exponential which is simply multiplied with a kind of a linear function t here. So what would be the response for this case? So if this sigma is less than 0, so you will ended up with this kind of a function. So with this overshoot, and you have kind of a decaying function. So this overshoot is basically due to this linear function just to multiply the exponential. So it's like this, like for example, so you have exponential function here. So this exponential is something like, let's assume this is the exponential function. And with this t, so the linear trend is like this. So we know that exponential functions are decaying very fast. So then if you just multiply a linear function with exponential, so in this first set of values, so this t, this linear function is basically dominating the trend, linear function is dominating the trend. But with the increment of t, so this exponential function is dominating the entire response. It means like if this exponential is immediately decays to 0, no point of having this large values coming from this linear function. For example, this is 1000, but at that time if it is like 0.001, so this the multiplication of this function 2 is simply uh, suppressed to 0. So the values are basically close to 0. So whether this linear function is dominating in the first set of t values, the exponential is rapidly decaying to 0, and as a result of that, so with the increments of time, with the large values of t, so your exponential is significantly dominating the response, and the ultimately your response is following the exponential trend, not the linear trend. But for the smaller values of t, yes, t is the linear function is dominating and response is aligning towards to the linear. So that's why we have a kind of a overshoot there, and then we just become a kind of a exponential trend. So the other case also, you can, if you plot it, it's something like that. So initially there may be a kind of overshoot here and like this. So this is like a sigma greater than 0. This is sigma less than 0. So, but we know that, so we are not interested about these type of responses because these are unstable set of responses. So these are unstable. So these are stable. Because we know that with the natural response, it should decay to 0. So if you observe these responses, these are basically converged to 0 with time. So this is also converged to 0. This amplitude also converged to 0. This is also converged to, so these are set of stable responses, and these are not stable responses. So if you are dealing with a stable response, so either this would be a response. So if you see this kind of response, you can immediately come to a conclusion. So this is a kind of second order scenario where you have this real and distinct roots. So if you see this kind of a second type of signal, so you know that, so the roots of this one is basically complex and conjugate. So then you know that this is a kind of under-damping system, and the third would be a kind of a critical damping. So you have overshoot and see. So with these characteristics, you can see like there are some information you can easily trigger it from this one. For example, the third case. So you have overshoot. So let's assume this is your current response. So if you know this IMT, so the height of this overshoot, so you can design a rest of the system, because without knowing this overshoot, the height of this overshoot, so you cannot design a system, because you know that this is not just a kind of a exponentially decaying function. There is a kind of a overshoot in between the short values of t. So it means like once you switch on the system, so your current is just jump into a kind of a value and then decays to zero. So then your circuit should basically handle this sudden increment of this current. So the design should be basically aligned to cater for this kind of a peaks. So even this one, so we know that once you switch on this one, this is the amplitude of the circuit current. So later on it may decay to zero, but so initially, so this is the current. So then your system should basically manage or survive with the high current. So if you are not designing the circuit for these kind of peaks, once you on the circuit, once you switch on the circuit, so definitely it will burn, because it cannot tolerate this kind of a high current, right? So that's why we need this kind of analysis before designing a circuit. So if you know these properties of this response, what would be the peaks values, what would be the uh, response time and so on, we can design a kind of a proper system. Otherwise, the rest of the electronic component may suffer due to this kind of a scenario. So that's the whole purpose of analyzing a electronic circuit by plugging this mathematics stuff. Yeah, so then this is the scenario. So the third, so we can take another special case where you don't have a kind of a damping. So for example, the one scenario can be obtained from this one under damped. So what about, so then this is for the second case where theta less than 1. So your roots are basically sigma plus or minus j omega. So what? So there may be two scenarios where one is like sigma not equal to 0 case. So then you have a real component as well. So then you have this exponential term in front of this cosine sigma. So the second case, sigma would be 0. Your real component is 0. Still you have complex conjugate roots, like for example, like j and minus j, 2j minus 2j. So these are complex conjugate pairs, but you don't have any real component in that complex numbers. So for this case, obviously, so this response is aligned to extend this model. So for this first case, so this is the response. What about sigma equals 0 case? So if your sigma is 0, so this becomes 1. So then your response is like a kind of a cos omega t plus theta. So if you plot it, so it's something like that. So I'll plot it here. So if you plot it, it's something like that. Isn't it? Because a response is a kind of cosine or sine function. So then what about the amplitude? This is again a kind of unstable system because your amplitude is basically in between a kind of fixed set of values, +1 and -1. So it's oscillate between the +1 and -1. We cannot see any kind of a stable output. So once you take a sample, so it may be +1, the other sample may be -1, so the rest of the samples may be between +1 and -1. So it's basically oscillate between +1 and -1. So this is basically oscillate between +1 and -1. This is again not a stable system, but we know that due to this oscillation, we know that the current or the voltage fluctuation is within that limit. So we know that it's just 1 ampere minus 1. Fluctuate between this. So nothing to worry. But we can manage or we can design a system for this kind of a undamped scenario. So this is called undamped case. So where you see sigma is 0. So in that undamped case, you have kind of a oscillating response. So it's basically, the amplitude is basically in between +1 and -1. So we have 4 type of systems: overdamped, underdamped, critical damped, and undamped scenarios. So depending on the sigma and omega or the characteristic of these roots, so you can basically classify it under overdamping, critical damping, or underdamping, or in certain cases, special cases, undamped scenarios. So with those response scenarios or the cases or the groups, so your response would be simply different from one to the other. So then we can simply say that, so if you just get the roots of the characteristic equation, you can immediately predict the response. With if those roots are real and distinct, you can just replace the response, natural response, as a sum of two exponential. If those roots are complex and conjugate, you can just plug this e to the power sigma t into a cos omega t plus b sin omega t model. If those roots are equal, so you know that this is a critical damped scenario. So the response is like k1 e to the power sigma t plus k2 t e to the power sigma t. So if it is a kind of a undamped scenario, so you know that this, it's a kind of a special case of this underdamping. So then your response is something like a cos omega t plus b sin omega t. So you can take this responses without deriving it. So but you have to get the roots of the characteristic equations. So then you should clearly mention that these roots are real or distinct, real or equal, complex conjugates, and so on. So then you can take the natural response or the format of the natural response immediately and find the unknown coefficients. So the then actually, so if I go to this slide number 13 in the second order circuit, so you can see a kind of a circuit having the resistor, inductor, and a capacitor, which is basically plugged into a kind of a voltage source. So then, so you can easily evaluate the current response. So it's something like so. So the response of this current is d squared it over dt squared plus r dit over dt plus 4 times it equals 0. So this net. So if you just get the characteristic equation, this is like s squared plus r s plus 4 equals 0. So then depending on the different values of resistance, so you will basically ended up with different scenarios. So this particular slide discussed, if you just propose a resistor of 4 ohm, so it basically aligned to a one system. So for example, okay, so this is like, what about like if you propose R equals 4 ohm. So then these roots are basically -2. So you will basically ended up with a kind of a real and equal root scenario. So then the response would be like this: k1 e to the power -2t plus k2t e to the power -2t. So this is the response for this. So if you basically select a resistance value which is greater than 4, like for example R equals 5 ohm, so then you will ended up with two distinct roots. S is basically -1 and -4. So then the response is basically move to k1 e to the power minus t plus k2 e to the power -4t. So then initially your response is something like that. So now your response turn to this model. So if you basically select a kind of less than 4 R equals, like R equals 2 ohm. So then your roots are like -1 plus or minus root 3j. So then the response would be something like that: e to the power minus t a cos root 3t plus b sine root 3t. So that the response is something like that. Okay, so if you select a kind of a resistance of 0, so then this response become, the roots become plus or minus 2j. Then the response is simply moves to k1 cos 2t plus k2 sine 2t. So then the response is changed this one. So see, like if you change the resistance value, if you change the resistance value, so this is the nature of the response. So it starts with overshoot. So if you, for example, if you connect a potentiometer, variable resistance, so you can just start with 5 ohm. So then like 4 ohm, then you can set it to 5 ohm, then your response is like exponential. So you can again bring back to 2 ohm. So then you have kind of a oscillation or type of a function decay into 0. So then you set it to 0 resistance. Your response is like oscillation function in between +1 and 1. So by changing your resistance for this particular case, you can tune your circuit to different scenarios. So the ultimate conclusion here is by selecting proper set of values, inductors, capacitors, and resistors, you can tune or design your circuit to operate in either way. So it may be a kind of a critically damping scenario. It may be a kind of a over damping, under damp or undamped scenario. So you can basically fine tune the scenarios by changing the resistance. But again, you can perfectly design a system by changing the rest of the values like L and C. But the issue is like, so these inductance and the capacitance, so it's hard to um, have a kind of a range. So for example, you can easily get a kind of a variable resistance, but so if you want to get a kind of a variable capacitance or variable inductor, it may be a bit hard in practice. So you can find certain variable capacitors and variable inductors, but the values are not that accurate and it's hard to find it as well. But you can easily find the variable resistor and plug it to the circuit and fine tune the circuit to get the required response. So this is the whole idea about this discussion. So how we design a circuit with a suitable response by adjusting these parameters of the circuit. So the next is actually I'm referring the slide 15. So we know that, so in the right hand side of the differential equation we have this force term. So from the beginning onwards we discussed this. So if this force term is basically 0, we know that there won't be any sources plugged into the system, so you can easily get the response. The response is basically depend on the natural response only. So if you have a constant in the right hand side of the differential equation, we know that, so we have basically external DC sources. So then the trial solution would be a kind of a constant for this forced response, and we can easily find the value of this constant, and the ultimate response depends on the sum of the natural response and the forced response. If the right hand side is a kind of a time dependent quantity, so you have to propose a suitable trial solution which is basically aligning with the general form of this force term. If it is like a ft equals t, so if you have right hand side, so t, so this is a linear combination, so you can propose like a t plus b model. So then you have to evaluate a and b together. So if it is like t squared, so this is the quadratic form, so you have to replace with the general quadratic term. So if it is an exponential, so you have to replace it with the exponential with the same order, so you can't change this exponent. So if it is a cosine function, so you have to replace it with more general trigonometric form, a cos omega t plus b sine omega t. So I have to keep this frequency same. So likewise, so you can basically change your proposed response, forced response, by looking at the force term. So depending on the force term, you can basically propose different type of forced responses and then find the unknown coefficients which basically involved in that. So in general, the total response, so xt is like the sum of the natural and the forced response. So what I want to emphasize here, so the ultimate response is the sum of these two quantities, natural response and the forced response. So you should be clear on how to evaluate this natural and forced response. So in the natural response, you don't have any option rather doing it in a time domain. So you know that you can take the left hand side of the differential equation, then take the characteristic equation and roots of the characteristic equation, then get the natural response depending on. So for the forced response, so you can again work in time domain by proposing a suitable trial solution by looking at the force term and find the unknown constant, or else you can convert it to the phasor circuit and immediately get the response, or the by solving it in a complex domain or phasor domain, so and get the response. So here you can do the time domain analysis or phasor domain analysis. So in this case, you have to get the phasor circuit and do it in complex domain. So this time domain approach is very straightforward and we discuss it. So we have two options to find the forced response. Either you can switch it to phase domain, or else you can be in the time domain and solve the forced response as well. So this is the very briefing for the second order circuit. So then we'll move to special scenarios. So I'm referring the slide number 17. So these are kind of special cases. So what it mean by special? So we know that for any kind of a circuit, so the ultimate response is equals to the natural response plus the forced response. So there may be some special cases where your natural response is included in your forced response. So there may be special cases where your natural response is already embedded in your forced response. Or else, like, you can claim that your part of the natural response is a subset of this forced response. So we'll take one example. Okay, so I am referring the same examples there. So we have kind of a differential equation like this. Okay, so by looking at this, you can get the natural response. So you can just focus to the left hand side by letting the first term to be 0. So then you have kind of this kind of a differential equation. Equals 0. So then you can get the characteristic equation. So s squared plus 3s plus 2 equals 0. So then the roots are basically -1 and -2. So then the response, natural response is something like that. K1 e to the power minus t plus K2 e to the power minus 2t. So this is the natural response. Okay. So what happens if I try to evaluate the forced response? So the forced term is 6 e to the power minus t. So then what would be the proposed forced response? So it's like a kind of a constant e to the power minus t. So then what happens? Like if we basically evaluate the value of k, so here in the natural response also we have this e to the power minus t term. So then it means like the natural response is basically embed this forced response itself. So you cannot have a forced response separately. So this forced response is already embedded in the natural response also. So it's basically treated the forced response also. So if you find the k and just plug it to the system or the equation, so you can basically simplify this k e to the power minus t, and ultimately you have two exponentials. So then this whatever the proposed forced response is automatically absorbed to the natural response, and you can't see any impact on forced response. So then ideally for this kind of scenarios, this is not the trial solution. Hope it's clear. Because it's already there in the natural response. So if your first response is already there in the natural response, whatever the proposed solution is no longer be a solution of this particular special scenario. So then what we can do is we can linearly increase. So you can introduce a linear term. So now the second proposal will be kt times e to the power minus. So then again check with the natural response and see whether this whatever the second proposal is also subject or embedded in the natural response. If not, you can take it as a trial solution. So for this particular scenario, it's not. So this is the trial solution now, not this one. So the simple briefing here is, so you can, once you get the differential equation, you can easily find the natural response by converting it to the characteristic equation and plug it to the standard formulas we derive based on the nature of these roots. So then you can evaluate the force response. So then what we can do is we can just go through the force term and propose a kind of a trial solution for this particular circuit. So once you propose these, so you have to check with the natural response whether that proposed solution is already there in the natural response. If it is not, so you can keep that trial solution as it is and assume that it's the solution for the circuit. But if this, whatever the proposed force response is already there in the natural response, so you cannot treat this as the trial solution for the special case. So you have to introduce a t term, or kind of a linear function in between. So then it would be kt times e to the power minus t. So then again you have to recheck with the natural response whether the new proposal would be there already in the natural response. If it is not, so you can keep that as the new proposal as a exact trial solution. For example, let's assume like if it is also there in the natural response, so you can increase the power of this linear combination. So instead of t, you can propose kt squared et. So you can basically propose kt squared e to the power minus t if this kt e to the power minus t is there in the natural response. So then again you have to check with the natural response whether this whatever the proposal for the force response is there in the natural response or not. If it is not, you can keep it as the exact solution. Otherwise, so you have to increase the power of them. So then you have to move to kt cube e to the power minus. So likewise, you can linearly increase your power of this force response term and get the exact force response or the trial solution for the force response by looking at the natural response as well. So then keep in mind, like you cannot immediately confirm your force response without evaluating the natural response. So ultimately the conclusion here is you cannot just say that this is the force response, but if I ask to evaluate the force response without uh, knowing, without evaluating natural, you can just think of, so this would be the force response. But if I ask you to evaluate the entire response, so you have to evaluate the natural response, and once you propose a trial solution for the force response, you have to check whether this whatever the proposal is already embedded in the natural response. If it is there, so you have to just introduce a linear term, t term there, and propose a new. So if it is also there in the natural response, so you can gradually increase your order of this theta and switch it to a kind of a better trial solution, which is basically not replicating the natural response. So you can just go through this couple of examples which I discuss here. Special case 2. So if you go to the special case 2, you can see like your force term is a kind of a constant 2. So if you propose a force term, so then it's like a constant. But if you evaluate the natural response, you can see like, so the characteristic equation has two roots, but they are basically zero. So if I go through this example, So this is the differential equation. D squared Vt over dt squared equals to. So natural response, how to get the natural response. So this is the corresponding differential equation by letting the first term to be 0. So then the characteristic equation is actually this. So here you have 0 as a root. So for this particular case, we have real and equal roots. Okay, so we know that if we have real and equal root, the natural response would be k1 e to the power st plus k2t e to the power st. So now s becomes 0, so this response is simplifies to k1 plus k2t. Now this is the natural response. So then we'll evaluate the forced response. Now this forced term is actually a kind of a constant. So we can propose our forced term Vft as a kind of a constant k. So see, like if once you propose this one, so there is a constant also here in natural response. So then this is not a solution, not an ideal solution. Why it's so? So this is already embedded in the natural response. So then we'll move to the next trial. KT. So once you check it with the natural response, again it's there in the set. See? So this is again not an ideal solution. So then we'll move to the next trial. Yes, once you check with the natural response, you can simply claim that it's not there in the second. So this is the ideal solution. So then your response would be Vt would be K1, K2t plus Kt squared. So you can find this K value by just plugging to the original differential equation. So once you plug it to here, so you have d squared over dt squared kt squared equals 2. So it's like 2kt. So then two k yes. So I got k as 1. Yes. So then it would be like this. So this is what I want to highlight. So once you propose a forced response, so you better check with the natural response whether it's there or not, whether it is forced response is part of the natural response. If it is part of the natural response, whatever the proposal would be not the ideal solution for this differential equation. So you have to modify or propose a next solution, and likewise you have to check with the natural response and simply find out which would be the exact or the ideal trial solution for the forced response. Okay, so this is the end of the second order differential equation stuff. So you can basically go through this slide set and the videos, and if you have any questions we can discuss it later.